Okay, everyone. Let's wrap up our conversations. Okay, awesome. So first of all, please start scanning the QR code. Very important for attendance. I see a lot more people now, so that's good. But a quick recap of last session, which was on Friday. We basically just talked about homotopic, heterotopic, enantiotopic, and distereotopic. So on a scale of 1 to 10, how comfortable are we with those? Do we do some practice problems?
Yeah, we need practice.
Okay. 1, that's not target.
3.
3.
I would
That's fine, better. We start with 1. So. Okay. So, okay. So today your professor actually went into a lot of the content for chapter 9. He talked about the 4 basics of NMR, and then he gave you the approximate chemical shifts, right?
Yeah.
For both HNMR and CNMR. I told you guys that it was going to be very important. Like you saw in these practice problems, like you have to guess the approximate chemical shift.
Yeah.
Okay. Now, quick update on SI. So I'm not sure if they're letting me be hybrid this semester, but they created a Canvas score for me. So I'm recording this session right now.
Yeah.
Don't get that excited yet. I'm not sure if it's gonna be available for you guys, but I'm recording it. So in case they say no, I can post it somewhere else so you guys can access it. Okay. So yeah,
Thank you.
I'm gonna try to facilitate that. But hopefully that's gonna solve some of the issues. Like if you have some schedule conflicts, that's gonna help you. Okay, but let's go to the handout. Okay, so this is where we left off, chemical shift. I pretty much just told you to memorize that entire chart, specifically the ones that are highlighted in yellow, okay? Because again, remember, you have to guess the approximate chemical shift, yes.
This is in Canvas right now, right?
The handout, yes. Yes,
With the notes on it and everything, right?
not yet.
No, okay.
Once I'm done with the entire handout, you guys are gonna have the copy of this in Canvas, okay? Okay, so let's talk about one tricky example, but I think you guys got it in lecture. So for example, if we're comparing this aliphatic structure, the one on the left, let's call it,
Can you explain one more time what aliphatic means? I know he said alkyl, but what does that mean?
so yeah, aliphatic, alkyl, they're the same fancy word at the end.
What is
They just mean that it's a carbon chain, and that's it. It's a pure carbon chain, a hydrocarbon more specifically. So carbon, hydrogen, that's it. Okay, so let's start with those two. So those two molecules are going to be considered to be technically shielded. Now, why wouldn't the ketone be de-shielded if we have that carbonyl area? What do we think?
Because the electron cloud density is closer to that environment. You asked the question.
Yes. So that ketone, it's technically in the aliphatic region. So it's not that de-shielded, it's mostly shielded. But we have that carbonyl area, like in their aldehydes, carboxylic acid, those guys. Those guys are extremely de-shielded. So why is the ketone not in that area?
Far away. It's kind of like if it's not off of the first carbon, you know, the first carbon hydrogen connected to, and then the second step, that second step.
Beautiful. Yes, you got it. So yes, let's look at our ketone right here. That carbon in red. It's very important. Why? Because it's gonna serve like a roadblock. So it's gonna prevent that de-shielding effect from the carbonyl area. So that means that we know that we have a dipole moment right there, right? It's just your carbonyl. It's very electronegative. We love it. But because we have the carbon in between the signal of those hydrogens, the de-shielding effect is not gonna be that great. It's gonna be still a de-shielding effect, but it's not gonna be as much. So if we know that the aliphatic region is between 1 to 2.5, that ketone will be more around 2.5. Okay. Now, if we compare with the other molecule, molecule number 1, it's just pure carbons. We don't have anything that's de-shielded in it. We don't have any electronegative atoms, nothing that's electron dense, right? So it's going to be closer to 1 in this case. Okay, so that's how you're gonna figure out the approximate chemical shift. Yes. I'm sorry?
Okay.
Yes.
yeah. So we would think that if there was, that methyl group wasn't there with that extra carbon, that would be in the 9 to 12 range.
Because that would be an aldehyde. Mhm. You got it.
The same, yeah.
So yeah, and that's it. So far, questions on that? This is pretty much just memorizing. So you guys can do some flashcards. Yes.
So on the test, we'll get that chart.
No, 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 no. You're not gonna get any charts for this exam. The only thing you're getting for the exam is the periodic table. That's it. You guys have to bring your calculator. Now, talking about calculators, let's see what he's gonna ask you as far as math related stuff. Oh, and actually, that's the little review that I did for you guys for IR. Now, you don't really have to memorize every single peak. The only ones that you have to be really aware are, of course, the ones around 1300. Why? Because that's your OH group. So we know that it's going to be a very broad peak right there. So it's going to tell us a lot. You can either have just a normal alcohol or you can have a carboxylic acid. Now, if you have the carboxylic acid, we have that carbonyl, that double bond area. So that means that we have to see a sharp peak around 1700 approximately. Okay. Now, yes.
Isn't there a difference of age? Without- staggered on?
The one that's staggered is usually correlated with the carboxylic acid. The one that's just like a big U, that's just a normal alcohol. But still, sometimes that can be confusing because IR is not going to be really that with a high resolution, let's say. Okay, but again, you're going to get IR clues just as extra. Okay, the main clues are going to come from HNMR and CNMR. Okay, so you don't really have to memorize every single little peak for IR. Got it? Any questions on this? Yes.
So all we should know is that the OH peak is at 3000.
Yes, you should know that one and the one for double bonds. Very important. And another very important one actually is going to be this one, your aromatic rings. We know that they're going to be really small stagger peaks. That's indicating a benzene group, and that's it. Okay, those are the three main peaks that you have to recognize. But again, if you don't remember any of that, you're going to be completely okay as long as you know how to read an HNMR chart. Okay? Okay, so let's move on to the math part. Okay, let's do this one over here. Now, yes.
Is he gonna give us like all three spectra aspects of complicated like that?
He could, yeah. Now, usually that's not a question that you're gonna get in the exam, but you might get it in your weekly assignments. Okay, but again, it's very possible that he gives you that. Or instead of giving you the spectra, he's just gonna give you the data. Like you have X amount of signals, this is the multiplicity, this is integration. Same for HNMR, CNMR, and he could give you some clues of IR. And some things even mass spec. So yeah. Okay, now, this is gonna be the only math part related for this class, okay? You're only gonna need the calculator for the first exam and that's it. Okay, and we have to memorize a formula for the ppm values. Now, the formula that's in red. So please memorize that one. So your ppm value is always gonna be equal to the observed frequency over the frequency spectrum. Now, keep in mind that everything has to be in hertz. Okay, that's the main part. Now, sometimes you're not gonna be given everything in hertz, so you're gonna have to do some conversions. So that's why I gave you that. 1 megahertz is gonna be equal to 10 to the 6 hertz. Okay, it's very important that you guys know that conversion. Okay, again, the only math that you're gonna see. After this, we're done with math. Okay. Now, let's try to solve this problem. So in this case, they're asking us for the observed frequency, which is right here. So that means that we have to do some rearrangements that are just basic algebra. So the observed frequency is going to be equal to the ppm value times the frequency spectrum. And again, everything is in hertz. Now, it says that you're given a chemical shift at 1.25 ppm. So far, those are the clues that we have. And then last one, it says that we're using a 400 megahertz NMR spectrometer. Again, very important. So now we have two numbers and we just need to find one more and that's it. So now this is the time where you're just gonna plug in the numbers. So in this case, remember, we're trying to find the observed frequency. And now let's just plug in the numbers. So ppm value, 1.25 times the frequency spectrum. Now, the frequency spectrum is given in megahertz. So you have to be careful because we have to convert everything to hertz. So how would I do that? Am I gonna divide it by 10 to the 6 or multiply it? You're gonna multiply it, beautiful. So yes, you're just gonna do this, 10 to the 6 hertz over 1 megahertz. So now we can see how the units are just gonna cancel and that's gonna give us the hertz. In this case, we have 400 times 10 to the 6 hertz. Okay, now that we have everything in the same units, now we can plug it back in. So it's gonna be 1.25 times 400 times 10 to the 6 hertz. So now, very last thing that you have to do is just plug in those numbers into your calculator. Yes,
Wouldn't you do 1.25 equals, X over the frequency?
yes, you can do that as well. But at the very beginning, I rearranged the equation. So it will be easier to just plug it in.
Oh, okay.
So yes, you can do both ways, whatever is the best for you. That's completely okay. That's why you have the answer key. So after you plug in everything, you should get a value of 5. What did we say? 500. Yes. This is 6 hertz. Now, sometimes in your exams, you're gonna see the answer choices as megahertz or hertz. So please read each of the answer choices properly, okay? Take your time because that's just gonna be an easy mistake. Okay, now, again, only math that you have to worry about. Most likely, you're only gonna get one question on this. So if you don't have a calculator, if you don't feel good with math, don't worry about it. It's just one question and that's it. Yes,
So in megahertz, it would be 5 megahertz.
it should be 5 megahertz. Okay, now let's talk about this part, which is actually important. Now, in this case, instead of solving the question, we're gonna talk about the concepts behind them. Okay. Now, let me pull up this. Okay. So in this case, sometimes you're gonna get asked which is gonna be the most D-shielded signal or the most downfield signal. You have to remember both terms. They mean the same exact thing. So downfield just means D-shielded. What about upfield? What does it mean? Shielded, beautiful. Okay, now in this case, you're comparing both in CNMR and HNMR spectrums. Remember that in that table, the values are not the same. What's the main difference between the values of ppm between HNMR and CNMR? What's the ranges? Exactly, yes. The ranges are way bigger for CNMR. HNMR, usually you're just gonna go up to 14 sometimes, 14 ppm. For CNMR, you can go up to 200 and more, okay?
Wouldn't it be the same for HNMR and CNMR? Like, I know the ranges are different, but wouldn't the downfield, the furthest downfield be the same for both?
Let's talk about it. So in this case, again, we're just looking for the most D-shielded molecule that we can see. Now, as we can see, the answers are not the same. So let's look at those molecules, number 5 and number 2. So we're comparing a ketone with a carboxylic acid. So now we might start to remember what we talked about at the very beginning of the session. So ketones, we have that carbonyl area, that's D-shielding. But if we're talking about HNMR, we know that it's gonna fall under one of the shielded areas, okay? So that's why the most D-shielded area should be number 2 for CNMR. What was the range for ketones in CNMR? Look at your notes. 100 and what? 9 to 12 is
That's
your
for
aldehydes.
HN.
Yes, it's for HNMR. What about CNMR? What's the approximate chemical shift? Ricky, 190, exactly. Now, if we look at the approximate chemical shift for H&MR, same molecule, it's gonna be around 2.6. So we can see that this one, it's really shielded. It has a lower number. Now, this one is gonna be different. It's gonna be more shielded. Now, keep in mind, H&MR, we're only looking at hydrogens, just hydrogens. CNMR, we're only looking at carbons. So if we start with carbon CNMR, let's just start with the carbon. That means that we're looking at this carbon and this carbon, between the ketone and the carboxylic acid, right? Now, once you know that, you have to memorize the approximate chemical shift for both of them. Okay, so you have to know that for your carboxylic acid, it's gonna be around 180, and for your ketones, it's gonna be around 190. Now, it would make more sense for the carboxylic acid to be more de-shielded because we have those two oxygens, right? But this is gonna be the only exception to the concepts that we've talked so far. Okay, so please memorize those exact numbers. Okay. Now, if we're talking about H&MR, now we're only talking about hydrogens. So that means that we're looking at, whoops. Let me do this again.
What's the reason for that exception? Or it's just the exception? Like we.
For CNMR values, it's just what they see in practice the most. So there's not an exact reason behind that. As far as I know, I'm sorry? Not really, because you have more dipole moments in the carboxylic acid. So it would make more sense for that one to be more de-shielded. But in practice, we see that the ketones appear to be more de-shielded. It's just a 10 ppm value difference. So it's not that much. Now, the exact why, I don't know. Are you gonna get asked questions on that? No.
Yeah.
Now, H&MR, we're only talking about hydrogens. So for the ketone, we're looking at that red hydrogen. For the carboxylic acid, we're looking at that hydrogen right next to the oxygen. So we can see the obvious difference. The one in the carboxylic acid is really close to something de-shielded. So of course, it's gonna be more downfield. Now, the other one, it was the example that we talked about at the beginning of the session. You would think that it would be de-shielded because of that carbonyl area. But again, we have that carbon in between. That's a roadblock. So the de-shielding effect is not going to be as high. So that's why it's going to be considered one of the most shielded signals as far as H&MR goes, comparing all of those. Okay. Now, usually you're not going to get asked to rank different molecules like that. Okay. You're mostly going to get asked questions on the approximate chemical shift and multiplicity. And then sometimes he either might give you a lot of questions with the spectrums themselves. So please start practicing that a lot, because you either run out of time or you get confused between the different ppm values. Okay. Okay, so far, any other questions on this one? I'm sorry? Start focusing more on how to read the spectra. Okay, because you're not gonna get a question like that on the exam. It's too simple for him to give you that. Yes.
How many carbons away is it considered a roadblock? Just one carbon away to roadblock?
Yeah.
So then it won't be in that 9 to 12 range. Instead, it'll be in that 1 to 2.5 range.
Mm-hmm.
So that's like the what's that?
Mhm. It's the alkyl area / aliphatic.
But it'll be closer to 2.5 because that aldehyde is still, that double bond to oxygen is still there.
Exactly. So yes, remember, everything is going to be up to what kind of molecule you have and what's surrounding it. Okay. So don't always assume that ketones are going to be around maybe 2.5. Maybe you're going to have a carboxylic acid adjacent to it, or something that's very electronegative that might raise it up to the heteroatom region. Okay. So it's always going to be dependent on that. Okay. Now, talking about multiplicity. Let's start with the one that you guys know, normal splitting. Okay, because there's a complex one. Okay, so let's start with multiplicity. So multiplicity, remember, it's just all about your neighbors, right? So we're just counting the neighbors, and then we're plugging them into a little formula. What's that formula? Beautiful, n+1. Now, the splitting. Am I gonna see it in both HNMR and CNMR?
Yeah.
Yes, no?
Different
No.
splitting.
Okay, how many of you think you're gonna see it in both?
Oh, no,
Raise your hand.
Mark is only, singlets, right?
It's just
Yeah.
singlets, exactly. So yes, we're only gonna see it in HNMR. And you're never gonna see splitting for CNMR. Okay, now, let's start with the first molecule over here. Okay, so first of all, how many signals do we see? 5. What do we think? Does everyone agree? 6? 6. 6, 1, 5. Okay, so let's look at those guys.
Yeah.
Oh, yeah. There's one extra H here.
Uh,
Now, is that gonna affect the number of signals?
Negative.
Nope. Now, we have a little aldehyde right there. That's gonna be signal number 1. Next ones are gonna be those 2 hydrogens, signal number 2. Next 2 hydrogens, signal number 3. Now, why is signal number 2 and 3 different? Why wouldn't they be part of the same signal? If they have the same number of hydrogens, the same structure? Beautiful. So remember how, so remember how NMR is always gonna be about the distances of how far away you are from something that's de-shielded. That's gonna affect the number of signals and the approximate chemical shift. Okay, so keep that in mind. Okay, 4th signal. We have the little hydrogen. And now we have those hydrogens. Now, why are they the same?
Because they're
all
equidistant from,
carbon.
yeah, they're just,
And you can rotate.
yeah, you could. rotate.
Beautiful, yes, that's a magic word. It can rotate. So this single bond, remember, that is gonna be able to rotate. So both of them are gonna be signal number 5. Correct? Okay, now let's start with signal number 1. What's gonna be the approximate multiplicity for that one? How many neighbors do I see?
Triplets.
So it's gonna be a triplet, exactly. You're just gonna plug it in, so 2 plus 1, of course, it's gonna give you 3. So you have to use the appropriate term for this part. So it's just a triplet. Do you have any questions on how we found out the neighbors for that signal? Exactly. Now, what were some of the rules that we had to follow for multiplicity?
Only beta hydrogen,
Only beta hydrogens, or how would you simplify that?
neighboring carbons. One carbon out, only one carbon out.
Yes, remember that your neighbors can only be 3 bonds away. That's the max. If you go 4 bonds away, that's not gonna be considered a neighbor. Okay,
Can you explain that like in practice?
yeah. Okay, so let's do it with this one. So again, we're trying to find the multiplicity for that signal, right? So we're just gonna count how many bonds away the other hydrogens are. So 1 bond away, I touch 1 carbon. 2 bonds away, I touch another carbon. 3 bonds away, I touch those 2 hydrogens. So because they're within 3 bonds, I'm considering them as neighbors. So I only have 2 neighbors. Now, questions on that? Yeah.
Doesn't matter which signal.
As long as they're from a different signal, you're good.
The signal 1 is a triplet.
Signal 1 is a triplet. Okay, now, what about signal number 2? So everyone agree? Yes.
Left, one, right.
What do we think? Quintet or quartet? Oh, okay, yes, don't confuse those terms, but you are correct. They are a quartet.
Signal is in there as well. Why is it a quartet?
We're looking at signal number 2.
Oh, so it's the one on the right and then the other 2 that are, got it,
Mhm.
okay.
So 3 plus 1 is gonna give you a quartet. Remember that quintet means 5. Okay, so please be careful with that. Don't worry. There's a quintet. Pentet, you don't use that term. You have to say quintet instead of pentet.
Signal 3 is.
What do you think of signal 3?
Sextet.
Septet, same? Quartet,
Sextet.
sextet, quartet, signal number 3. How many of you think it's a quartet? Raise your hand. How many of you think it's a triplet?
Oh, wait.
We're looking at signal number 4.
Wait, Vortex.
Sorry, number 3.
Signal 3 is a quartet.
Quarter. Quarter.
Because it has 2 on the right and 1 on the left.
Beautiful, you guys got it. Yes, I was just trying to confuse you. Okay, what about signal number 4? What's that?
Signal 4. Yeah, sextet.
Sextet?
Signal.
Do we all agree?
You got 3 on the left.
No? What do you think? How many neighbors does it have? 8? Yes.
On it.
Sorry? Yes, you can do every single path possible. Mhm. You got it. Non-F. Okay, so let's wrap up our conversations. Come on. Okay, everyone.
Sextet. It's not right.
Whatever works for 9, whatever works for 6.
Wait, it's not right?
So in this case, remember, for this class, you don't have to specify the exact name of how many neighbors you have. Once you go past 5, you're just gonna say a multiplet. So technically, you're all correct. Some of you are slightly wrong on the number of neighbors, but
What's the number of neighbors?
for this one, let's look at it.
Signal 4.
We have the 6 hydrogens for both methyl groups, remember?
Oh.
And then we have those 2. So at the end,
8 neighbors.
mhm. So signal number 4 is technically gonna be a non-F formally, but in practice, we're just gonna call it a multiplet. Anything higher than 5, yes. Okay, and last one, signal 5, what is it? Don't worry,
Over how many?
over 5. Question,
Wait, what is that? What's signal 5?
mhm.
How do you know it's signal 4?
You're counting everything. If you're touching a carbon, you're touching a carbon. If you're touching a hydrogen,
Signal 5.
that's gonna be a neighbor, but it also counts as 1 bond away.
5. Because signal 5, there's 2. Signal 5. Yeah.
Oh, I'm so sorry. So number 1, we're doing that, 1 bond away, I touch the carbon. 2 bonds away, I touch the second carbon. 3 bonds away, I touch 1 and 2 hydrogen. So that's how I got it. So 2 plus 1 is gonna give you a triplet. You're going to, you're always gonna go to every possible path. Beautiful, you got it. How bonds away would that be? How many bonds away?
What's
Mhm. So in this case, if we're looking 1 bond away, touch a carbon. 2 bonds away, touch a carbon. Mhm. You're always starting from the 8. 1 bond, 2 bonds, 3 bonds, 4 bonds, that's when I touch. Exactly, beautiful. Okay, last, yes. On which one?
Are we done?
This one, I'm so confused how this is more downfield, it's like how 5 is more downfield than CM.
So that was the only exception to our normal explanation for the issue. Mhm. So yes.
No, what about?
Okay, everyone, signal number 5, what is it? Triplet, doublet? Doublet?
Doublet.
Beautiful, you guys got it. It is a doublet. Because you only have 1 neighbor, which is this little baby hydrogen from signal 4. Let's do this. So I touch that hydrogen. That's where I'm gonna start counting the bonds from. 1 bond away, I touch a carbon. 2 bonds away, I touch a carbon. Now, can I go down?
No,
Yes.
same signal.
Because they're part of the same signal, they're never gonna be neighbors. So you're only gonna go to the right. So that's 1, 2, 3 bonds away, I touch a carbon. But also 3 bonds away, that's where I touch that little hydrogen that I have. So that's my only neighbor. Questions on how to find the neighbors? Very good? Okay. Now, I'm gonna give you guys 5 minutes to try and find the multiplicity for all of the signals in both molecules. You guys can work with each other, talk to each other, it's completely okay. 5 minutes again.
5 minutos.
Exactly. Yep. So I'm using those names after I get the number from the formula that I plugged in, which is n+1. So if we look. Okay, let's look at the hydrogen
No, because I got the one.
that is on the second molecule, the last ones that are drawn. Okay, so those ones, there are 2 hydrogens, they're not gonna be neighbors to each other. 1 bond away, I touch the carbon up there. 2 bonds away, I touch that carbon in the carbonyl area. 3 bonds away, I touch another carbon. So far I don't have any neighbors. And then if I go again to the carbonyl area, 3 bonds away up, I touch an oxygen, so that's not gonna be a neighbor. So I don't have any neighbors. So now I have to plug in that number into the formula, which is n+1. So it's gonna be 0 + 1, which is just gonna give you 1. Now, for multiplicity, we're not gonna say the exact number. We're gonna use the same 2 words. So singlet, doublet, triplet, those guys. We're getting fancy with chemistry. No problem. Yes. Oh wait, I'm good. So sorry.
Oh.
No, no.
Mhm.
Hydrogen's on the ring. Same.
They wouldn't be the same. This one is closer to the benzene ring. This one is closer to that isopropyl. So they don't have the same environment. They're not supposed to do the same thing, even though they're both equally to that carbon area.
Okay, so.
Are these?
That's 1 bond away, 2 bonds away,
Further away from it.
3 bonds away. That's your map. You're touching a carbon, so no neighbors to the right. Because remember, your neighbors have to be within 3 bonds. If they're at the 4th bond, like those hydrogens, they're not gonna be considered neighbors. No neighbors to the right. What about to the left?
So there's one.
You always start from the signal. So 1 carbon, sorry, 1 bond away, you touch a carbon.
Go, have.
2
Without.
bonds away, carbon. 3 bonds away, hydrogen, beautiful. You only have 1 neighbor. So now you plug it in into your formula. So 1 + 1 gives you 2. What's the name for 2? I'm gonna write them down for you guys. You can have it as rest. It's a double.
Right.
Mhm.
Okay, so that's one.
And there's a 2A. That's one. They have the same distance.
But one is closer.
You don't have to know, like, you don't have to identify if it's gonna be 2.4, 2.5, 2.6.
But I thought.
You have, it's gonna be up to what's nearby. So in this case, that ketone, that carbonyl area, is causing that de-shielding effect. So that means that it's gonna bring the number closer to 2.5. If we compare with this, just pure carbon chain, we don't have anything that that's negative. So it's gonna be closer to 1.
Next.
You got it, no problem. Yes,
Wait, I need to.
No, they're different signals, for sure.
you got it. Beautiful.
Okay,
Give me 1 second.
really?
Yes,
So they,
so sorry that I take so long. Don't worry, there's another. Oh, don't
Because
worry.
there-
Welcome.
In the three-dimensional space, they're like.
Oh, that's
this.
completely
It's
changed.
lots of them.
That's completely.
They're like this.
So they're the same.
They're like this. They're like this. Like, no, no, they're like stripes.
Too fast, okay. So far,
Those two.
you can always raise your hand and I can repeat everything or rephrase it in another way. Yeah, which is good, but always like start with the SI handout because it's a more friendly format. The SI handout, this paper that I'm projecting right now, always start with that one. It should be under files and it's gonna be a folder called SI Fall 23. So you can always access all of them right there.
No,
Yeah.
no, keep talking about the
Talking about
actual
the-
So yeah, always start with that. Why? Because we're gonna talk about the concepts, explanations, all of that. And then if SI is going a little too fast for you, I can either slow it down. Now, if the slowing down doesn't work for you, you can also go to tutoring. We have tutoring available for free. So it's really good. No, yeah, don't worry. The weather wasn't cooperating.
Yeah, so. Yeah, like there's
Mhm.
something. Yeah, it's like.
You always go to any path possible. In the case that we did, we couldn't go up or down. So it's always gonna be up to the molecule that we have. Mhm.
No, but we have.
Mhm. And you can also go up, but in the case if you go up, you're touching the same signal, so they wouldn't be neighbors. So it's always gonna be up to one kind of molecule. Yeah. Let me do this problem so I can show you better what I'm talking about. Okay,
Someday. They like a word.
okay, everyone, let's wrap it up. Let's come back. Now, I couldn't get to the questions of every one of you, so sorry about that, but right now we're gonna go over the practice problem, so we have enough time to cover the complex multiplicity. Now, really quickly, let's start with the second molecule. First of all, how many signals did we find?
6.
8, 7, 6, 6, 7,
Nah, man, 6.
yes. Which one? 9, 6, 8. Okay, we're getting all of the numbers at this point,
What
so
is it? Enlighten us.
let's look at them. So,
Tell me.
let's look at them. Calm down, people. Okay, so we're gonna start with the little method groups. Are they gonna be the same signal? Yes, because single bonds rotate, right? Beautiful. This is gonna be just signal number 1 and 1. Baby hydrogen right there. Signal number 2. 2 hydrogens right there. Another signal, so number 3. Now, the next 2, are they gonna be the same as number 3? Why? Exactly, yes. Remember that even though they look like the same signal, why? Because they have the same number of hydrogens, we have to see what they're exposed to. If they're not exposed to the same thing, they're different signals. So that's number 4. Next 2 signals. Number 5. Yes.
So stay on either side of that, double bond to carbon. If this.
Left one.
No,
This end and that benzene work like a spin by like hydrocarbon, that they have longer hydrocarbon on each side.
If they had different numbers of hydrocarbons in between,
Yeah.
different signals.
They're just rather than those two.
They have to have the same exact group on both sides. There has to be symmetry. If there's no symmetry, they're not the same. Exactly. So, yeah. Okay. So right now, 2 things can happen. Question. It doesn't matter. Okay. So technically, there are two different answers for this one.
What?
It has to do with the resonance, yes. Now, we talked about this at the very first few sessions. Now, remember, Benson rings for this class are gonna be a little bit special. Why? Because sometimes we're just gonna see them as a multiplet, meaning that every single hydrogen that you see in there is only gonna be one signal. Now, that's in practice. So let's just start writing that. This is gonna be number 6, signal number 6 in practice. Now, theoretically, remember that word, theoretically, that means that we can see every single signal separate from each other. So that's when we can see the signals like we saw them in Orgo 1, meaning that these two hydrogens are gonna be one signal, so they would be 6. Next two hydrogens, number 7, beautiful. And then last one, number 8.
Not crazy, is it?
Why is the last one 8? Why would it not also be part of that?
They're not gonna be part of the same signal. Why? Because they're exposed to different distances to the other.
Oh,
So the rest.
that's-
Exactly, yes.
So,
Technically, they can be the same signal.
So what's the correct answer?
6.
Well, if I were to take this on a trend.
Okay, chill, people. Let's calm down.
Okay.
We're getting a little too competitive right now.
You playing, right? Fuck you, Stan.
Okay, so final answer for this molecule. 6 signals.
So it's 6.
It's 6. Why? Because you never saw in that question theoretically or theoretical. So you're just gonna assume that they're gonna be part of the same signal. Yes,
And it's 6. You was wrong.
yes, you're gonna assume that it's 6 unless that he specifies that you can see all of the signals separate. He has to specify. If he doesn't specify it, you're just gonna assume it's the same signal. Okay, questions on that? Yes. 6. Final answer, everyone, 6. The ones in green, that's just your theory. That's what we learned in Orgo 1.
Yeah.
In practice for Orgo 2, it's just gonna be 6. So final answer is gonna be in pink. That's it. Green is theoretically. In theory, yes. So those of you who said 8 or 6, you guys are correct. Those of you who said 5, 7, and 9, you're not that quite right. They're both technically correct. Yes, you do. Okay, let's start with the multiplicity really quickly. Just tell me left to right. First signal, what is it? Doublet. Signal number 2? Nonet or multiplet, exactly. Number 3. Number 4. Beautiful. Number 5. Triplet. And then very last one, 6. You got doublets and triplets, yes. But combined, what are you gonna see in the actual spectrum?
Just one single.
What's the word? I'm looking for a specific word. Not a singlet. Which one? That's the definition of the molecule. But how am I gonna see the multiplicity of that molecule in the spectrum? A shift, triplet,
Where does it?
Wait, number
No.
3, Alex?
we're gonna talk about that. But the first one, this one, remember, benzene rings in practice, they're always gonna be shown as multiplets,
Why?
no matter what you have around. It's just, give me 1 second. This one is just gonna be a multiplet. Now, technically, we can see that some of the neighbors around could be considered as neighbors. But what's gonna happen is that all of those separate signals, they're gonna be clustered together. Why? Because we don't have the best resolution on our spectrometer. So that's why at the end, we're just gonna consider it as multiplet, because in practice, once you see the spectrum, it's gonna look like this. Just a bunch of signals just clustered together. So you can really tell what's gonna be the multiplicity. So that's why we just call it a multiplet, because that's what we see in practice with the spectra.
What's the reason? Or we don't need to know.
You don't need to know the reason, but the reason is because we don't have the highest resolution of our spectrometer. The higher the resolution, the more separate you can see those signals. But again, you don't really have to know that one. Question. Very good. Okay, now let's talk about signal number 2 or 3. Which ones did we have a question on? No questions? Okay, very good. Okay, this one right there, the last one. First of all, do we see any planes of symmetry? Yes, so that's very important. Remember, that's gonna change the number of signals. Why? Because they're just mirrors of each other, okay? So in this case, you only have how many signals? What do you think?
4.
It's just gonna be 4. Those method groups, signal 1, baby hydrogen right there, number 2. Those 2 hydrogens, number 3, next 2 hydrogens, number 4. That's it. Okay, let's start with signal 1. What's the multiplicity?
Why are 3 and 4 different?
3 and 4 are different because they're exposed to different things. The one on the left side is composed of those 2 method groups right there, the isopropyl
Oh,
group.
okay, got
The
it.
other one is not.
Thank you.
Exactly. Multiplicity for signal number 1.
Thank-
Doublet, beautiful. Number 2. Beautiful. Number 3. Doublet. Last one.
Single. Oh, because you look at the left, not the right. So,
Doublet.
yeah. true.
Very last one, number 4.
Singlet.
It's a singlet. Exactly. There are no neighbors. Now, you can only go to the left side. On the left side, we don't have any neighbors. Now,
Question.
Yeah.
So, because it's dimensional, you can't go right, but in theory, you can still go right, so will it not get below? a
you could
signal?
go right, but at the end, they're not gonna be neighbors because they're the same exact signal. So there's no way they're gonna be neighbors of each other. Exactly. So remember, hydrogens that are part of the same signal, they're never gonna be neighbors of each other. Okay, please remember that. So again, the reason why you can go to the right is because that's a plane of symmetry. They're the same exact signal. Okay? Yes. Yes. Okay. Okay. We're gonna talk about complex multiplicity in the next session. I really wanted to talk about it today, but we didn't have time for that.
Thank you.
So get ready for that one. It's gonna be a new concept. I'm gonna do the IR story Wednesday. You should have told me when I was talking about IR. Yes. Oh, wait. It's a triplet.
So we don't have the one the aromatic ring, just one with the hydrogen, because I got 8.
No, they're not counted up.
One, and then
Why
we have the
signal
other
5?
One, two, three. If you go to the right, 1 bond away, you touch a carbon. 2 bonds away, I touch another carbon. 3 bonds away, I still touch another carbon. So there's no way that any of those hydrogens in the benzene ring are gonna be neighbors of signal number 5.
So for signal number 5, okay, let's say the ones on the ring are 1. We count them as 1, right?
Signal in the benzene ring, yes.
Okay, that's neighbor. So that was 1, and
Can you
then.
explain what's
signal number
1?
4 has 2 hydrogens. That's two.
What's
That's
1,
not
2?
right?
Like,
No.
No?
So remember, we're just looking at number 5. This hydrogen. 1 bond away, I touch a carbon. 2 bonds away, I touch another carbon. 3 bonds away, either if I go up or down, I still touch carbon, so no neighbors to the right. Because you're only gonna touch the hydrogens once you go 4 bonds away, which is breaking the rule. So that's why.
Got it.
No problem.
Thank you.
Questions? This one, because it has 9 neighbors in total. So whenever we have the answer as 6 or more, we're just gonna call it a multiplet. You don't have to say a specific name. So if we're looking at signal number 2, 1, 2, 3, 4, 5, 6, 7, 8.
I feel like the strawberry combined or they're
Yes.
separate? Strawberry.
You got it. No problem.
Never mind.